Welcome back. This is chapter 6.2, Signals and Systems and Transform. Today we'll talk about DTFS, DTFT, some tables, the properties and examples. In the first 6.2.1, we'll talk about DTFS of periodic signals. Specifically in chapter 6.2.1, we'll introduce DTFS of complex exponentials and sinusoids by direct applications of the analysis equations. We examine spectral leakage, we inspect the synthesis equation, and we see the periodic nature of CKs. Now we know that DTFS is applied only for periodic signals. So the periodic signals we are going to first examine is the simplest one, the complex exponentials and sinusoids. The simplest complex exponential that we will study is this one. It has an amplitude of 3 and it is rotating at 0.2 pi radian per sample, and it has a phase shift of minus 0.5 pi. There is an angle of plus, means that as sample n grows, you will realize that the complex exponential is rotating anti-clockwise. Now let's plot amplitude 3 E plus J 0.2 pi n minus 0.5 pi as n goes from 0 to infinity. This is the figure. On this axis here, it is the real axis, and on this axis here, it is the imaginary axis, and on this axis here, it is time growing from n equals to 0 to n equals to 15. So let's see where is the first point. I'm going to use a green circle here, and I will tell you now that this is at n equals to 0. So if you plot here, you will realize that it's n equals to 0. It is along the real axis with amplitude at minus 3, and angle is minus j pi over 2. How did I get this number? Well, if you substitute into this equation for n equals to 0, you realize that this guy goes to 0, and it is 3e plus j minus 0.5 pi. So this is exactly 3e minus j pi over 2. In fact, if you substitute different n, you would be plotting this phasor that is rotating anti-clockwise with magnitude 3 with different phases. You can plot the real part and the imaginary part as well, or if you prefer a polar plot, you can see this. Now in a polar plot, because the phasor is rotating over each other, you have no idea where is n equals to 0. So let me show you where is n equals to 0. It is here. So the magnitude is 3 and the angle is minus pi over 2. So this is n equals to 0, n equals to 1, n equals to 2, n equals to 3, and so on. How many points does it take to rotate one full circle? We can count 4, 5, 6, 7, 8, 9, and then at n equals to 10 it repeats itself. So how do I get n equals to 10 is the period? Well, what you should do is that you know that at every sample as it increases, we are moving by pi over 2. So it will take 10 steps to rotate 2 pi. Alright, so anyway, we're back to this question. We're given this complex exponential. The most direct thing for DTFS you can do for yourself is to generate xn, the complex exponential sequence, for one period. So in this case, you can generate 10 samples and then apply the DTFS equation using n equals to 10 and then generate ck, and ck, remember, is the equation. It is this equation here where we calculate ck using this equation. Now if you do that, you'll get the correct answer, but for complex exponential, there is a much easier way. Okay, so let's figure out. Right, what I'm going to show you is that we're going to compute this using n equals to 10, generate the CKs, and out comes the result of the magnitude and the phase spectrum. So this is the magnitude spectrum here, and this is the phase spectrum here. And remember that for DTFS, along the horizontal axis is k, where k equals to 0 until n-1, where n equals to 10, so it goes from 0 to 9. And then this is the phase plot. So again, we have the horizontal axis 0 to n-1. Now in the magnitude plot, what do we get? We get only one single line at k equals to 1. And at k equals to 1, the value is 3. What is this 3? Well, remember that the complex exponential have magnitude 3. So you are saying that at k equals to 1, we have magnitude 3, telling us that exactly this 3 here. Well, then there's a phase shift of minus 0.5 pi. So at k equals to 1, there is a phase shift of minus 0.5. So it's with respect to pi. Everything else is 0. So in fact, this plot shows you exactly this equation. So what do you think k equals to 1 is telling you? K equals to 1 is telling you at the frequency omega equals to 2 pi over n times k. And what is n? Is 2 pi over 10 times k is 1. So this is equals to 0.2 pi, which is exactly, again, this value, 0.25, 2 pi. So this figure and these values that are non-zeros is telling us exactly these coefficients 3, 0.5 pi for the phase at frequency 0.2 pi. So this is the interpretation. Alright? So this is C case. Now, sometimes, I'm telling you that 0 to 9 is with respect to 2 pi over n times k. So once in a while, I would actually plot for you directly the value. So k equals to 0 means 0 radian. 1 means 2 pi over n times 1, 0.2 pi radian. So this is 0.2 times pi with respect to pi. Second one, 0.2 pi times 2, 0.4 pi, and so on. So the second figure here, this column of figures, is exactly the same as these figures, except the horizontal axis is now changed to radian per sample. So let me write it down. Radian per sample on the right hand side, and on this side is k with respect to k. Now, some small point, if you are going to use MATLAB to try to generate this, you'll realize that there are some values over here, and it is random because it's due to numerical precision. What you should really do is to zero out the value. So anything, the absolute value of ck less than some value, will zero these guys out using this equation over here. You can use my MATLAB examples to see how I have generated this plot. That means by simply generating xn for 10 samples and using this equation to compute every values of ck. Now you must be wondering, what happened if I use n instead of 10 and I use n to be 100? I still can generate 100 samples, and because 100 samples is still periodic at 100 samples. If it's periodic at 10 samples, then it's still periodic at 20 samples and 30 samples and at 100 samples. So what's happened now? Well, I can generate 100 samples of xn by how? Simply just computing xn for 100 samples. Then I substitute this. So now I have different values here. This will be 100 and this will be n-1, so it's 99. And then I have x0 until x99. So I need to compute this, and I write a for loop there again to compute for k equals to 0 to 99. Now, so I've done that, and now you can see ck's going from C0 to C10, 20 until 99. Alright. Now, there's a difference now. In the previous example, we saw that the spike happens at 1. Now, the spike is happening at k equals to 10. So what gives? So this is k equals to 10. So remember that this frequency is exactly 2 pi divided by n times k. So this is 2 pi divided by 100 times k is 10. So this is still 0.2 pi, which is exactly this 0.2 pi again. Alright, now the amplitude is still 3 and the phase is still minus 0.5 pi. Alright, so this is a figure. And what about on the right hand side? On the right hand side, I converted k into radian per sample, and in fact what happened is that this is exactly again at 0.2 pi, but now it has more points in between as compared to the previous graph, and basically we have used n equals to 100. Therefore we are now doing more samples along this angular frequency. That's all. So the whole idea is that if you use a longer sequence, you are now actually computing this Fourier series across more frequencies. In this particular case, it's useless because everything else is 0. Now we're going to do something slightly different. We're going to use n equals to 101 now. You realize that well, what happened when we go from n equals to 100 to 101 for this particular complex exponential? Something strange will really happen. You realize that, okay, the ck goes from c0 to c100 now, because it's 0 to 100, so it's 101 pin. But our original data, there's no way we can calculate 0.2 pi along these frequencies. So what happened is that even though our real data is sitting at 0.2 pi, our analysis did not analyze directly at 0.2 pi. So what this caused is something called spectral leakage, and this is a real DTFS calculated using this equation, and you'll realize that our amplitude is now no more 3. In fact, it went down a little bit, and to 2.95. And where did the rest of the energy goes? It actually leaks to its neighborhood other bins. Okay, and this is called spectral leakage. This occurs when the power across the signal goes into the spectrum of other neighboring frequencies, because the signal being measured is not periodic at the interval of the frequency. So it means that at exactly this point here, it is not 0.2 pi. Alright, and that is why it leaks. Alright, so in these last few slides, we have examined the DTFS using this equation to compute the CKs for magnitude and the phase. Thank you.